So let's continue our discussion and finish out the program from the random walk. Um, so we already programmed problem 4 here last time we looked at this with the switch case, with this distance here. We have the switch case and case 1. Problem 5 is what we're going to do right now. I saw some people's solutions, they had a little trouble here. So reminder, problem 5, this is our probability distribution, which is this here, and you would graph that out. It's a triangle, right? So if you look, -1, 1, boom, and here's 1 here. So the first step here is we got to find the CDF. So the CDF is going to have 2 regions. So in region 1 here, and region 2 here. So let's find the CDF in region 1. CDF. So let's do the region 1. It's going to start from -1 to some x. 1 plus x dx. That's going to equal x plus x squared. 2 minus 1 to x. That's going to equal x plus x squared over 2 minus this, which would be this -1 plus half, so that's going to be minus a half. But you're minusing that, so that's plus a half, which equals 1/2. Factors out of here, so the x plus x plus 1 squared. Right? So I factored out the half here. X squared plus 2x, or this -1 appears to be -1 plus minus, so it's minus half becomes plus half, so that works out just fine. Okay, so then we need to do the CDF for the second region here, which means we have to start from -1, go to 0, which is this guy here, which you can just put this solution here, 0. So we'll just do this over here. Plus 0, 2x, this guy here, x dx. So I can just take this solution here, put in 0 instead of x for this part, so that's 0, minus the half, so that's just plus a half. Plus we do this, minus x squared over 2, doing that term first, plus x. Okay, which you can see here that we're going to have something very similar here. So let's just reorganize this. Equals half minus x squared minus except minus 2x, right? And then take the minus out, except minus 1. Okay, so this is very close to being x minus 1 squared, so we have to complete the square. So I want to make this -1 a +1. To do that, well, since this is actually plus a half, I need to subtract 1 and add 1. So I'm adding 0. This -1 is going to come in here, make this. So I'm going to put this in here. So that would make that -1, that would make that +2, which come here and make x squared minus 2x. You're adding 2 to this. So we make that +1, +1, which equals minus a half x minus 1 squared plus 1. Okay, so we have our two CDFs here and here. So we need to invert them. So let's put that down here. Okay, so I'm gonna change. So now I'm gonna change. So let's actually swim in here. So let's write down these two CDFs. So we're gonna call the CDF instead of CDF R because it's gonna be a random number, and we have 1/2 x plus 1 squared, and this is region 1. So this is when x is between -1 and 0, and then we have R equals 1 minus 1/2 x minus 1 squared. So this is -1, 0, 0, 1. And this will look like half -1 to 1. So in this regime, it looks something like this. It goes right, and it comes over here and pink. There's that 1. Okay, so now we just have to invert this guy. Well, so look at region 1. It's from 0 to a half. Would be this one. So when R, so let's invert the first region, which is when R is between 0 and half, which is this thing here. So we end up with 2R square root. All right, 2 comes over here, square root, get that, -1 equals Rx. Now let's test this. When we roll a random number of 0, which is here, we should end up at 1 here. So if I put 0 here, I get -1, that's great. If I roll a probability of a half, I should not move. Half makes this 1, square root of positive 1 minus 1, 0. Good. So that's good. So put a box around this one. We're good to go. Check. You always have to check. In the other region, where our probability, our random number, could be 1/2. 1. So, okay, we have R minus 1, and then times 2 minus 2 equals x minus 1 squared. All right, so I minus the 1, flip this around, and got that. Okay, so then I take the square root. So let's see here if this makes sense. Can I take the square root of this? This is going to be between, this is between half. So let's just commute that in here. So we're going to end up with 2, 1 minus R equals x minus 1. Make this check. R is going to go from a half to 1, so this is going to be going to 0 to 1. So this will always be positive, so it's safe. Take the square root of this, and go ahead and erase this 2 here. Okay, and you're like, oh, so now you say x equals the square root of 2, 1 minus R plus 1. Now, does that make sense? Well, let's test it. If I put a half in here, I should get a 0 out. I put a half here, which makes this a half, which makes this whole thing 1. Square root of 1 is 1 is 2, so that fails there. If I put 1 here, I get 0, which makes this 1. So it fails here. It works here. So something went wrong. Well, we have to. This is what's going on. You have an exponent of 2. So if the one solution doesn't work, do the other solution. There's 2 solutions. So you could just put a negative 1 in here and do that. So we could, instead of negative 1, we could do minus 2r minus 1 equals 1 minus x. Equivalent, right? All I did is multiply by negative 1 here. Negative 1 squared is 1, so really I just multiplied by 1, right? Yep. So, okay, we take the square root. So, the square root with 2r minus 1. 1 minus r. 1 minus r equals 1 minus x. So that 1 becomes a negative. So I have negative 1 plus square root of this, square root of 2, 1 minus r equals negative x. Let's just erase that. So we need to change the order of these things. So let's just do that. So, oops, didn't want to do that. Hit PowerPoint. Sorry about that. Find a place here. Okay. So we're going to end up with, so that becomes negative, but it becomes negative. So it's 1 minus the square root of 2, 1 minus r, square root. Okay. So let's check this. This is an equivalent solution to this because all I did is minus 1 squared in here, right? Minus 1 is 1, so I multiply by 1 because it's squared. So I'm just taking the other solution. Let's see if that works. I put r at a half. So a half, 1 minus a half is a half, times 2 is 1, square root of 1 is 1, 1 is 1 is 0. We come over here, when we roll a half, here, we should have 0 here, good. Now let's put in 1. 1 minus 1 is 0, so this whole thing is 0, this thing becomes 1. So when I roll a 1, I should end up at 1. So yes, this is my solution for when 1 half r 1. I saw some people try this in their code, and it was all messed up and they couldn't figure it out. Check your solutions. Always make sure the limits make sense, because we're got a square root here. 2 solutions. One of the solutions might not make much sense. Not give us what we want for an inverted CDF. Okay, let's go ahead and program that in here. Okay, and it's exactly the same setup. There we go. It's exactly the same setup here, right? We're going to have 2 if statement, or if else statement. If that, if we're in this range, which is r is less than a half, our displacement becomes square root 2 times r, oops, minus 1. Okay. And if we're over here, we are 1 minus the square root of 2 times 1 minus r. And that's it. What? Oh, yep, I actually have to call r. Good job. Yeah. See, I'd have to actually call an r. I call it in case 1, but I didn't call it in case 2. Okay, it's giving me a warning about a y as an unreferenced variable. That means I don't use it, so I can just get rid of that. Okay, let's go back to our main. So there's where all the motion happens. Good. So what's next? We have to do the variance. Let's see here. Look at the assignment. We want to find D. We want to analytically solve for D. Well, we know. Let's look at that. So a new page for this. Okay. So when we know for random motion that the variance theoretically should be 2 1dd t. Also, the variance is defined as and since we're x of n is just going to be theoretically infinity x to n px dx. So since these are symmetric probability distributions, both for the coin flip and for the other one, we pretty much say, hey, this integral should be 0. So really what we want is the second moment. And so let's look at that for the coin flip. Well, the coin flip is the discrete, so this becomes essentially two delta functions. So you have -1 squared, and you have 50% probability there, plus 1 squared, 50%. And that's per time step, which just gives you 1 plus a half plus half, which is 1 per time step. So 1 times t. Each individual roll is a separate thing. So if you want to track this with time, it's just multiply t right there. So then you can come here and say, oh, that equals 2d. T's cancel out. Obviously, d is a half. And most people got this. This is easy stuff. Let's look at the other one. So x squared, we actually have to do the integral to 2 parts, -1 to 0, plus x squared dx, plus 0 to 1, 1 plus x squared dx. So we have x squared here, so we're going to end up with x cubed 3 plus x cubed fourth to 0 plus x squared x3 3 minus x 4 4 0 1. Okay, let's move this down. Okay, so let's come over here. Well, that means we have 0 minus, doing this one here, minus 1 comes in here, that makes that a minus 1/3. It's a positive fourth, plus 1 comes in here, that's a 1/3, that comes in here, fourth, and then 0. Okay. That, obviously there's no 0 here, so we end up with, come here, this makes that a plus, so we have 2/3, that makes that a minus, minus 2/4, which is a half, so which equals common denominator. So I'm going to multiply this by 2, 2, 4, 6, minus, multiply this by 3, which is 3, 6 equals 1, 6, which equals 2 dt. And again, this is per time, so it's multiplied by time to get per step, because every individual step's an independent thing. So it's just the variance is just be variance for one step times t. So d equals 12th. So we need to measure the variance. And I'm going to do the 3D motion and the 2D motion here, or the 3D motion and the 1D motion. 2D, this current homework. Okay, so how do we want to do? We want to do it for every time step. We want a variance. That way we can have a an array we can print that's just time versus variance. Again, and from that we can fit it to get our d. See how it compares. So first of all, I'm going to make another array to fit my variances. So I will call it lowercase variance, and I'm gonna make another definition here for my time. Define another constant definition. Oops. And we're going to do 100 time steps. We should call that's an actually variable, so I'll call time end. 100 time steps. This should go to t end. And I'm going to make a variance that goes to t end. Build. Haven't done anything with that, that's fine. Now I'm going to make a function to find a double. Let's do it right here. Double let's call it VR, and it's a variance of my walkers. What is it going to take? It's going to take in a double array of my walkers. And that's it, because I've defined the number of walkers I have. So in this case, 100. And let's just set that up right now. Double I'll just come there. So would you make a function and you just don't want to, you want to just set it, so we set double, want the variance, set that equal to 0, and we're going to return the, okay, so we haven't quite coded this, but we could still use it here. I'm going to just, how we're going to use it, right? So we're going to say, hey, the variance at time t equals VR, and we're going to input x. So this is how we're going to set it up. So all we're doing here is that for a given situation here, here's what problem we'll be doing. The case, for a given case, let's go to randomly walk, set it to case 1, and it's going to spit out the variance. And we can look at it. And obviously when I print that double array, so at the end we want to print out the variance, which is a variance. And what's the size? And so now, once we program this variance function, that's it for problem 4 and 5. Okay, good. So let's go ahead and print that. We also want to have, how do you want to do sum? A lot of people like to use sum equal to 0 and sum 2. I've seen that a lot. That's fine. Equal to 0. Oh, and we want an integer. I like to just do all my variables at once. So we want to do a for loop. For I equals 0, I is less than n, I plus plus. Okay. Sum equals sum plus our position. Sum 2 equals sum 2 plus our position square. Oh, I said W. These are not X in the main, but W here. Because it doesn't matter what you call it here, as long as what you pass through is what you want. Okay? And then sum equals sum divided by n. And sum 2 equals sum 2 divided by n. And of course, we have to return our variance. V equals sum 2 minus sum times sum. Okay, let's actually do case 1 with, say, 100,000 walkers, and we'll just do time t. So build and start the button, and hopefully everything works. Okay, it seemed to work. Well, now we'll go to the folder where it's at. Okay, so we'll find it, random walk. TV array, this is it, that's what I paid. Told it to do, and you see it's essentially, let's copy. You can see it's linear, 1-to-1. But let's go ahead and graph it. So I just copy and paste. Import paste. Boom, boom. Highlight it real quick. Insert scatter plot. Let's fit it. We want linear. Display. I'm going to set the intersect. You can come here. Format trend line. Set intercept to 0. There we go. 1. Okay, so that's 1. So 1 times time, x is time here. So that means 2d. That's a half. Good. Let's get to this. Let's go back to our case. And we're going to set to case 2. So just to double check here, case 2 is this guy. Start debugging. Okay, and it ran pretty fast. But you see, I did 100,000 random walkers. The number of random walkers is kind of more important than the time. We're trying to model aerosol, right? So aerosol is millions of particles in the air. But it's the same, so we did that one. Let's do the same procedure. Okay. So we got different here. And let's do the same thing. Let's add goes to 100. Okay, much less. Set the intercept there, linear, let's just display. Okay, well, we know it's supposed to be a 6th, so it equals. Yep, very close, 1.666. So that's dead on. So D is 12th. That's how you do the 1D case. Let's go ahead and now do the 3D case. So I'm going to go ahead and stop. So this is, I'm going to comment 1D. And so I would copy and paste this. So this is the 1D. Now imagine I copied and pasted this, and now I'm doing a new project, or I have another if statement or something like that. I'm not going to make another project. Let's just do, now let's do 3D case. Okay. So I saw a couple different things here. I saw people do it on Lattice where they selected either X, Y, and Z, up, down, left, and right for the case 1, and then do something special for the other case. I'm going to just do one case here. But I want to raise for my X, Y, and Z. And we're just going to repeat this bit of code. And Z. and of course this bit of code. So we're just going to see. Okay. And I want a few more variables here to help us out. We want a dr, we want a theta, we want a phi. Okay. So this distance here, whatever case, isn't our total distance now. It's going to be our dr. So we can just use that same case function. Say this time we use 1. And then we need to find our phi. So how are we going to do this? We can just do the random call from here. But we could also make this in our case statement. We could use our case statement again. So let's actually program it. I like that. Let's use it all in this case statement. So let's make another case. Let's make case 3. And this will be our phi. Oh, that's scant. I mean, yeah. And we want a random number, r. And then, we need to define pi. Because pi is not a default thing, so let's just go ahead and define a pi. Sorry, I'm taking so long here, but you can kind of see where this is going. I noticed some people had some problems with the 3D motion, so I'm gonna go. That's why I'm still going in pretty strict detail here. Okay, case 3, and then you just do 2 pi r. Right, 2 pi r. So distance equals 2 times pi times r. And then we can do a case 4 for our theta. And I talked about this to death, right? You have to do our random number, so r between 0 and 1, and so you're sampling cosine, theta, not theta. That takes a random number, makes it from 0 to 1, and then we're going to set our thing that's returned, which is just called distance, to a cos r. Okay, and it's complaining about theta is an unreferenced variable, but that's fine. We haven't defined it yet. I'm surprised it didn't fail because I didn't do anything here. So phi is case was it case 3? And then theta equals this case 4. So this is the case 1 or 2 is the movement. That's the only thing we have to change, so we'll do that. And so we have case 1 is coin flip, case 2 is sampling our distribution, case 3 is phi, case 4 is theta. Okay. X equals X dr times sine theta times cosine phi. Y equals yi dr sine theta sine phi, and then z equals z cosine theta. The spherical coordinates, and that's how we do the motion in 3D. So, and it makes it really compact, right? Because I'm using the case statement to kind of cheat, and well, not cheat, but I'm using the case statement to do everything. All my random sampling is in this case, switch case statement. So I call it here 1 because I'm moving dr in case 1. Phi is always going to be 3. Theta is already 4. But people did it all different ways. It's fine. And the variance is the sum of the 3 variances because they're independent axes. So I just find the variance of x, then I can find the variance of y plus the variance in z, and then I'm just going to return print the array. So let's do that. Let's do case 1 here. So we're going to do the coin flip, the analogy to the coin flip for random 3D motion. Okay, took a little longer. So try copy. Let's just. So this is 3D. So this is going to be 3D coin flip. Import delimited space because it's separated space. Sometimes you get data they separate comma or tabs, and we can kind of see it's the same as here. So this is, we'll call this chart 1D. So we might even do this 1D, and then we'll copy this chart. And then say, okay, this will be the 3D case. And you notice that, let's get rid of the fit. So you just, and if you want to do this, sometimes you just click on the data, you see, oh, look, there it is. So I can, if your data is not like a billion things, you can just, oh, I'm going to move this here, and I'm going to move this here, and it changes the graph. And you see it didn't change anything. So our variance still goes to this linear with time, but now we have a 6 dt instead of a 2 dt. So we just divide our 1/2 by 3, and you get 1/6 as your diffusion constant. So let's do the other case. It's 2. Build, run. Take a little bit because my antivirus is looking at it, but still it should be pretty snappy. And there it is. Okay, go to the file. So there it is. Oh, I should close the file. See if it actually had it open. Okay, good. All copy. See if this worked. So we'll just put this here. Well, it's interesting. You can see that, yeah, it's basically the same, but there's a little bit of difference. Okay, move this. There's the fit line. Move that there. And move that there. No visual difference. You get the same spin, which is a 6. So our diffusion constant is, divide that by 6, 136. And a lot of people got tripped up by that. Like, oh, no, that's the same. You're getting the same statistics, but since we have 3 degrees of freedom, we diffuse. It samples those degrees of freedom the same, but you have to counteract the diffusivity of the equation, so the diffusion constant is by 3. No big. So that's the 3D case.